You didn't reply to my email, but I said it was anyways.
Yeah, figured you would.
How's your thing going?
It's going all right. On you sent the email on Monday, right?
Yes.
Yeah. So on Monday, like I had to go to the IT department for over an hour on Tuesday because my email, like I could only receive emails, I couldn't send. And it was because they had made some changes over the weekend that completely broke Thunderbird's ability to log into our outgoing mail server. And so then after that, I forgot about it because I was so pissed off not being able to send email outs. So, yep, like I was over there from like 8 o'clock in the morning until close to 9:30 yesterday, and about 10 other people were on the phone saying like I can't send emails. So they literally had to just revert the changes that they put through because they could not figure out how to fix it.
They should wait till the quarter.
Yep, that would have been a smart move. Like, oh, it's close to finals week and we're going to do something with our email settings that might prevent, I don't know, instructors from communicating with their students. Let's do it right now. Yeah. But anyway, not that I'm salty about that or other things at all.
Which section are you 13 for 120?
Yes.
Okay, I was just gonna have to look and see what.
Yeah, I'll be there tomorrow to like pick up the tests or whatever, and then I'll just hand them off to you or Stan. Because I'm assuming I'll be with Stan again, or you will be with Stan, but that's who it was last time. He wasn't able to show up last time to pick up the tests, which is why I'm gonna stay, just so that you can kind of just pop in and do the thing. I feel like it's 4:30. I don't know, Mary will probably send an email.
That's fine.
Yeah.
What is Thursday? Yeah, I can just go get my extensions and then come back and get the test from them.
Okay. Oh,
So if you click on that, does it tell you?
turkeys.
Oh, no. Sounds like sick.
There are 2 more.
Oh my goodness.
Yeah, smoked 4 turkeys on Sunday.
I gotta make cookies today.
Did anybody else sign up for literally anything?
Okay, so I asked for a veggie or salad side. Dr. Crittenden signed up for green bean casserole.
Okay, well, a vegetable maybe.
Like,
I mean,
but I'm not gonna be upset because you signed up for something. Uh, Josh is bringing the salad. I'm bringing cookies, and Dr. Howell's bringing some
Okay.
dessert.
so the usual suspects continue to bring absolutely nothing. Cool. Let me mute this so it's not recorded.
If you click on that, does it?
Now I'm not gonna swear quite as much.
Okay, so I'm gonna give on this survey, and then I'm gonna send you the end of course survey, like the one where they just say like, what do they like, what do they not like, whatever. And you can just post that and send it.
How about, 'cause I'm this lazy, I just add you to my class so that you can upload it for me because I'm a bit overwhelmed right now.
AJ's there too. One of my students was like, "Are you teaching 223?" And I was like, "No." And he's like, "Why not?" I was like, "I've never shadowed that class ever, and I'm teaching this class. He's like, you need to teach it." I'm like, "Well, don't count on it."
Yeah, you're not going to teach it. You're not going to teach it until you have a PhD. Yep.
I swear, this thing's like,
Oh. 99% just going to reuse most of test three from last year.
the only thing, so I just have to, for whatever we're doing today.
Tell me how many new op-ed questions and stuff like that I need to put on there, if any, like what's going to make up your test. And then I'll just pull from old things. Okay.
And I just need to add like a conceptual question about what we're doing.
Okay.
And so it'll be about like cable.
Okay. All right, so it's close enough to 8, so let's go ahead and begin. Ms. Ward has something that he wants you guys to do, I guess.
Yeah.
She's gonna use a QR code, which means I have to disconnect my computer.
So if, hopefully y'all were here the first day I got y'all to do a survey. And so this is just the end of course version of that survey for my dissertation. This is extremely crucial, so if you could do it, I would just really appreciate it. If it shows up. Yeah, there it is. So if y'all could take that, I'd appreciate it.
I'll get my big head out of the way.
So don't answer it how you think me or Matt would want you to answer it. Answer it like how you actually feel about it. The only thing we're gonna use your campus-wide IDs for is getting your major and matching up if you took it the first day of class and the last day of class.
I don't know. Yeah, I don't pay attention to that. I don't know. So for me, because I record everything and arguably post the videos at some point sooner rather than later, a lot of students choose to attend asynchronously or just on Zoom. And so this looks, yeah, I mean, there's a few people at that table right there with Sabrina that aren't here, but they're usually here. So I don't think they dropped. If they did, they dropped it like 4 days after the drop date, which is not probable. Yeah. Yeah. So,
I do.
Oh, yeah.
so anyway. So probably somewhere between 1 and 15-ish, I guess, maybe. Something in that ballpark. I don't know. Doesn't matter to me.
So if y'all came in late, just take this. I'm also gonna post another survey that's less crucial, but definitely still helpful. It's just like an end of course survey, like what did you like about the class? What did you dislike? Things like that. I'm gonna post it on y'all's Canvas.
All right, so assuming all of you guys are wrapping up Miss Ward's quiz.
Thank you.
Now I want you to do an evaluation for me. So this is just the general end of quarter evaluation thing. Just they put it on Canvas instead of doing the dumb website or whatever, I guess. So it's on Canvas. It's literally at the very top, so you can't miss it. Log in, take a couple of moments to do it. I just want to see if it tells me how many people did it. It's thinking about loading stuff.
Oh, yeah, 8% of the students. There you go. Oh.
Monday.
All right.
Yep. See you later. Yeah. Just waiting for this to hit at least 50%, so my boss stops yelling at me to never because I never make my students actually do this dumb thing.
Oh, yeah, if they get 100%, are you?
Yeah, that's not gonna happen.
Because I'm a solver. I can give it to you.
Yep.
I can also answer it in the announcement.
Maybe, yeah.
So I taught 2 courses, like last winter and then spring. I have not gone any email.
Yeah, I think we're all aware of that. Yeah, that's not just you. It's text thing.
Yeah, then you have to. Oh, it's free for it. It's not very good. Yeah. Oh, I'm just curious.
I found an export one, I think it's really interesting, but yeah. I'm following that.
Yeah, you just refresh the page.
It is indeed. I'm gonna go use the restroom real quick while you guys wrap up on surveys. Before I get back here, we'll look over and.
Oh, yeah, that. The thing is, like, I knew when I was doing my hands, like, you were watching it. Like, I checked it, like, I checked another video, I did it by myself. Did I understand? I did not, and I did the same calculation problem. When they got my girl. And then I'm saying, like, where did you get this? Worst part is I had the same. No, we do. Not the one that's. I had the same steps. But I was like, I'm not. Yeah, the worst part was like, they're having to get to see. Don't, I think it's. I was like, wow. My homework. I think like question far away there. Yeah, rolling with the rounds. Actually, they're kind of like maroon. You were.
It's actually really fun. They opened it back up, but it was diesel. You could have been. That reminds me to make Captain that unit rights. So
I think I.
I never online, yeah. They're writing. Then they must be writing. Not here, they're writing.
Or like just for most.
Yeah, because that's where I.
Yeah.
But on the way back, I went.
All right, let's see what this is up to.
They,
All right, so let's go ahead and get started on today's lecture topic. So as I mentioned in our last class meeting, this is our last lecture, and it is on power factor correction. So when we discussed power factor in Monday's class meeting, we talked about how the power factor mathematically was the ratio of the average power to the apparent power. And this is equal to the cosine of our power factor angle, theta s. And then, if I'm not mistaken, I mentioned something about the fact that P, the average power, is what we as consumers pay for whenever we pay our utility bill. And apparent power, the magnitude of our complex power S, is what the electric utility pays to generate, okay? And so the electric utility wants the ratio of those two quantities to be as close to 1 as possible so that they're not wasting money and resources generating power that's just going to get sent right back to them, okay? I also mentioned, if I'm not mistaken, that there were effectively thresholds for the ratio that the power utility company would like to see. Typically 95%, 97.5%, something like that, okay? So if your power factor is below that threshold, you would receive a fine. So today, what we're going to be talking about is how industrial consumers, like manufacturing plants and stuff like that, correct their power factor to meet the threshold set by the utility company and avoid paying fines and all of that kind of good stuff. Okay. So I'm going to draw a power triangle representation for the complex power absorbed by an inductive load. Okay. So this is my imaginary axis. This is my real axis. And let's just say that this complex power, S old, represents the complex power absorbed by a load prior to power factor correction. So let me just write that down over here. So we can see, again, just using our power triangle relationships, that the projection of S old onto the real axis will be the real part. So that is our average power, P old, prior to power factor correction. We are going to have a projection onto the imaginary axis. That is going to be Q old. So that is our reactive power absorbed prior to power factor correction. And then lastly, we might have some angle here, theta old, representing the value of our power factor angle, once again, prior to power factor correction. Okay. So I want to ask you guys what I hope is a fairly simple and straightforward question. If we are trying to improve our power factor, and by that I mean make it closer to unity or 1, do I need to make that angle theta old larger or smaller? Smaller, because the cosine of 0 is 1, right? So there are 2 different ways that this can be accomplished mathematically, but in practice, one of them is completely and utterly asinine. So we'll talk about that one first, okay? So mathematically, this very much improves power factor, but it is a terrible idea to do this in practice, okay? So let's say that we were able to hold the reactance of our load constant, meaning we're not going to add any inductance or capacitance or anything, and instead we just added some resistance. So in that particular case, we would be absorbing more average power, and so we might have something like this. So this angle, theta nu, is smaller, and therefore our power factor has been correct, right? Since the angle is smaller, we're going to be operating at a higher power factor. Now, why is this the dumbest possible way to achieve power factor correction? The average power is what we as a consumer pays for. So we would be running up our utility bill in order to avoid paying a fine, which makes literally no practical sense whatsoever. So while mathematically this works, it is utterly stupid, okay? So a different way to achieve power factor correction, and the one that's actually utilized by industry, would be to lower the amount of reactive power that is seen in our system, or that is absorbed in our system. So let's consider the case where we hold our average power constant, meaning we don't introduce any new resistance and only try to lower our reactive power. So that would look something like this. So here's S nu, where S nu is the complex power absorbed by a load after power factor correction. So let me scooch this description down a smidge so I can write something here. Okay. So based on our power triangle, S old could be written as simply the sum of P old plus J Q old, right? That's just the rectangular components of our old complex power prior to power factor correction. And if we wanted to write a similar relationship for S nu, since we didn't introduce any resistance, or specifically we're trying to hold our average power to be constant, the real part of S nu is still just going to be P old. So now I'm going to simply identify the projection of that over here as Q new, so that we have S new is equal to P old plus J Q new. And while I'm at it, I'm going to go ahead and label theta new, which is just the power factor angle of our complex power after power factor correction. Okay. So this setup, now that we understand what's going on, we're able to lower Q. We will increase the power factor at which our load absorbs power while not changing our utility bill at all. So this is effectively a one-time cost, assuming that we always operate at this particular power factor. But anyway, so how do I lower the amount of reactive power that is absorbed in my system? So let's revisit some relationships that we learned towards the end of our last class meeting. Okay. Let me do these in blue. Okay. So when we have just a resistor, the complex power absorbed by a resistor by itself is the magnitude of the RMS phasor voltage squared divided by the resistor value, right? I mentioned on Monday that this quantity is purely real and it is always positive. So with adding resistance, lower Q, absolutely not. It will increase P. You got it. So let's just go through so everybody else can catch up. For an inductance, we got the relationship J times the magnitude of the voltage squared divided by omega L. So inductors absorb reactive power because it's purely imaginary and it's always positive. So if we added inductance, this would actually make Q larger, not smaller. Okay. So by process of elimination, the only way to make our reactive power smaller for an inductive load is to introduce capacitance, because the complex power absorbed by a capacitor is given by negative J times the magnitude of the voltage squared times omega C. So it's purely imaginary and it's always negative. Okay. So the complex power absorbed by a power factor correction, and I'm just going to write that as PFC capacitance, is S cap is equal to S new minus S old. Okay. And this should always be a negative quantity, because S new has a smaller value of Q than S old does, right? And so we can sort that out simply by substituting things in here. So S new, recall, is P old plus JQ old. And then we would have minus P old, sorry, oh goodness, what the hell happened there? Oh, actually this one should be new, my bad. Ooh. So the P olds cancel out and we're left with simply JQ new minus Q old is JQ cap, where Q cap is just the reactive power absorbed by the capacitor. And I'm just going to make a note here. Q cap should be less than 0. So we have some level of understanding of what the power factor correction process entails, in as much as we know that we're adding some amount of capacitance, right? So a couple of things that I want to discuss with you all is where we're going to put the capacitor in our system and how we're going to find out what value of capacitance to put in our system in order to achieve a specific target power factor, okay? So let's actually handle the second part first. We have two different relationships, one right here and one right here, for the complex power absorbed by a capacitor in a steady state sinusoidal system, right? This SC on the left is our generic representation when we know the voltage, we know the frequency, and we know the capacitance. And over here on the right-hand side is what we got when we are deriving our power factor correction relationship. So if we set those two equations equal to each other and solve for C, we can then determine what size capacitance we need to apply to achieve power factor correction, right? So the capacitance C needed for power factor correction is given by this relationship, where C is equal to negative Q cap divided by omega times the magnitude of the voltage drop across the capacitance specifically squared. The reason why there's a negative sign out front is because Q cap is always a negative quantity. And so this will return a positive value for our capacitance because we can't have negative capacitors. Another way to think about it pretty simply is we've got a negative sign here and not a negative sign on the other side of the equation. So there should wind up being a negative sign somewhere in the mix when we set those two equal to each other and rearrange. Okay. Now, this relationship works, but I don't particularly care for it because I am, generally speaking, too lazy to bother to solve for what Q cap is, right? So this relationship would be more useful to me if I could put things in terms of my current power factor and my target power factor, okay? And I can't quite make it that easy, but I can make it pretty damn close by relating things to our power factor angles, theta nu and theta old, okay? So that relationship is going to look like P old times the tangent of theta old minus the tangent of theta nu divided by omega times the magnitude of the voltage drop across the capacitor square. So now if I know what my old power factor angle is and I know what my target power factor angle is, I only need to know average power, which is constant for both things, my angular frequency of excitation, and the value of the voltage drop across the capacitor. So now let's talk about where we will apply our capacitance. Okay. So let's consider a simple system. On the left-hand side, we have some simple sinusoidal voltage source, which I'm going to represent as an RMS phasor voltage. I have what I'm going to loosely call a transmission line. Effectively, this is just a section of wire or wires that are used to connect our source to our load. And it may have some impedance that we have to care about, which is I'm calling ZW. And then over here on the right-hand side, is our load impedance. So this simple circuit diagram is representative of a single phase system where we are using a voltage source to supply power to some load. And I am taking into account the fact that the wires that connect my source to my load might have some impedance. Okay. So we have two options effectively. Okay. One option would be to place our capacitance directly in parallel with our load. Okay. So if we have a system where we have a motor or something simple like that, which is an inductive motor, which is going to operate at a lagging power factor just by its nature because it is an inductive load, we could put a capacitor in parallel. And what will happen is it will not change the voltage drop across the load literally at all, but it'll wind up lowering the amount of current that's flowing into the load, thereby causing it to operate at a lower power factor. Okay. There's nothing particularly wrong with doing it this way if you have a simple system and you've only got one induction motor or something like that that you need to correct for. But in an industrial setting, chances are you're going to want to do power factor correction for your entire plant and not on a load by load basis, because that's going to be an expensive thing to do. So instead of applying our capacitor across the load terminals, we would instead place it across our source terminals. So this is the situation that we are going to deal with explicitly in this class. Placing our capacitance across our source terminals, because this allows us to correct the power factor of the load, and also, for what it's worth, our transmission line impedance ZW is usually slightly inductive as well. So we are correcting for any contribution to a low power factor generated by our cables by doing this practice. So let's look at a simple system. Okay. So let's say that I have a 400 angle 0 degrees volt RMS voltage source, which is a voltage used in industrial applications. I have a transmission line ZW that has an impedance of, let's call it 0.1 plus J 0.05 ohms. And then, sorry, I made that line too big. We're connecting to a motor. Which has an impedance of 5 plus J3 ohms. So I want us to find C such that PF new is equal to 0.98 lagging. And then I want us to find C such that PF new is equal to 0.98 leading. The reason why I want to find both of those capacitances, and they will have different values, is because that's effectively going to give us a range of capacitances that would meet the requirements of the electric utility. The utility does not care if your power factor is leading or lagging. They just want it to be close to 1. So if our threshold for the electric utility is a power factor of 0.98, anywhere from 0.98 lagging to 0.98 leading would be an acceptable power factor. Okay. So the first thing that we're going to have to figure out is, oh, and I'm explicitly putting my capacitor here when I do power factor correction. Okay. So the first thing that we're going to have to do is analyze the circuit and figure out how much complex power our source is supplying so that we know what our initial power factor is. Okay. So anybody have any thoughts on how we could find the complex power supplied by our voltage source here? So if we use voltage division, that would allow us to find a voltage. I don't have a problem with that per se. I'm just interested to understand how you'd use it. So let me talk out loud here and just see if you guys are thinking about things conceptually the same way that I am, right? So we are correcting the power factor at which the source is operating because our capacitance is placed in parallel with the source. So I think, and you can tell me if you believe I'm wrong, but I'm not for what it's worth, that the amount of complex power supplied by the source has to be equal to the amount of complex power that is absorbed by our transmission line network represented by the impedance ZW and our motor represented by the impedance Z motor. So effectively, complex power supplied equals to complex power absorbed in our system. Does anybody have a problem with that? Because that's just the law of conservation of energy. So I feel pretty strongly that you should have no beef with it, okay? So then that begs the question, well, is there an easy way for me to figure out what the complex power absorbed by everything to the right of that capacitor is? And I feel like there is, because we know the voltage drop across those two impedances in series, and we know those two impedances in series. So I feel like that's enough information for us to calculate complex power, because we literally have a relationship that tells us S is equal to the magnitude of the voltage drop squared divided by the complex conjugate of the impedance. And we know the magnitude of the voltage, and we can get the complex conjugate of the impedance very easily, right? So I'm going to say that the complex power supplied by my voltage source is simply
the magnitude of Vs divided by the conjugate of ZW plus Z motor. And that guy up there should have a squared on it. So this isn't a new relationship. We're just applying it to this system where I have two impedances in series and I'm just being lazy. Okay. So anybody have any questions, comments, or concerns about this particular relationship? So since nobody's speaking up, let's go ahead and use this, okay? So what's the magnitude of my source voltage? 400 volts RMS. I'm going to square that. And now I'm just going to add those two impedances together. So 5 plus 0.1 is going to look like 5.1. I'm going to have minus here because I'm taking the complex conjugate. And then I have 3 plus 0.05. So I think that is 3.05. So when I plug that into my calculator, and I put my calculator back in degree mode, I wind up getting 26,925.002 with an angle of 30.881, so 881 degrees, volt amperes. So this guy right here is literally theta old that I need to solve for my capacitor value. For what it's worth, this value of theta old corresponds to a power factor old of 0.858 and some change lagging. I'm just mentioning that because obviously, since our target power factor is 0.98 lagging or leading, we want to make sure that we aren't already there and don't need to correct our power factor. But in this case, we quite obviously do, because 0.858 is less than 0.98. Okay, so we know theta old. We can also put this answer in rectangular form to find P old, because that's not going to change when we do our power factor correction, right? So in rectangular form, this looks like 23,107.965 plus J 13,819.469 volt amperes. And so this number right here is the P old that we plug into our equation. So I'm just going to scroll up here and see what else we need, right? So P old, check. Theta old, check. So we just need theta nu, omega, and the magnitude of the voltage drop across our capacitor. So for the omega part, that's just something that has to be given to us, and I forgot to give it to you. So let's go ahead and take care of that now. So this 400 angle 0, let's just say that we're in Europe. And so our frequency is 50 hertz. Okay. So this number is practically always going to be 50 hertz or 60 hertz if we're describing an industrial process, and it just matters on which part of the world we're in as to which value that we use. Okay. So European countries use 50 hertz. North America uses 60 hertz. All right. So how do I find omega if I know F? 2 pi times F. Absolutely right. So that is just going to be 100 pi radians per second. How am I going to find theta nu? Can anybody tell me that? Inverse cosine of our power factor. Okay. So this is going to be, and I'm putting a plus or minus sign out front here because I'm interested in knowing the angle for both a lagging power factor, which will be the plus sign version, and a leading power factor, which will be the minus sign version. So this is plus or minus the inverse cosine of 0.98. So that's going to be plus or minus 11.478 and some change degrees. Lastly, what's the magnitude of the voltage drop across my capacitor? 400 volts RMS. So when our capacitor is in parallel with the source, it's just the source voltage. So from this, let's put C lagging here. It's just going to be P old times the tangent of theta old minus the tangent of theta nu over omega times the magnitude of our capacitor voltage squared. Plugging in numbers, that looks like 23,107.965. Let's look at the units here just for the sake of argument. So that's going to be watts times the tangent of 30.881 degrees minus the tangent of positive 11.478 degrees, all over 100 pi radians per second divided by 400 volts RMS quantity squared. So if we look at the units here just really quickly, okay, we're going to have, do this up here, right? So we've got a watt in the numerator, which another way to think about that would be a volt times an amp, just for what it's worth. And then in our denominator, we have per seconds. So that's the same thing as putting a second up in the numerator as well. And then we're dividing this by volts times volts. So if I look at my units here, this volt cancels this volt, and my result is something that's in amp seconds per volt, which is literally farads. So dimensionally, this is going to work out. And now let's just plug stuff into our calculator, right? So 23,107.965 times the tangent of 30.881 minus the tangent of 11.478. Damn, input lag got me. Divided by 100 pi times 400 squared. I got 0.000181.582 farads, or 181.582 microfarads. So that is the smallest capacitor that will get me up to the power factor that I'm desiring. For our leading power factor, exact same equation, but now we're going to put in that same power, 23,107, excuse me, 0.965 watts times the tangent of 30.881 degrees minus the tangent of negative 11.478 degrees, because remember, a leading power factor has a negative phase angle. Divide this by our 100 pi radians per second and multiply it by 400 volts quantity squared. And I get 0.000368276 farads, or 368.276 excuse me, microfarads. So that's the maximum capacitance that would still provide power factor correction. Anything beyond that capacitance will actually push us so far into leading that we're operating below a power factor of 0.98. And when you guys do your lab, you will literally see something like that, okay? So the experiment that I'm having you guys do today is correcting the power factor for a simple RL network, resistance and an inductance. You're gonna hook things up with your oscilloscope, function generator, all of that kind of good stuff. You're gonna see when things start off that your current is lagging your voltage by a pretty significant amount. You're gonna put your first power factor correction capacitor in, and you'll see that that puts the signals almost exactly in phase. So you've corrected your power factor to something rather close to 1. And then when you put a second capacitance in parallel, that's actually going to push it so far into leading that you have a worse power factor than when you started with just the inductance by itself. Okay. All right, so get to it.